Lecture 38, and we were discussing liquid fuel combustion. And before we go to liquid fuel combustion, we thought we'll first study the simplest possible problem related to liquid fuel combustion. So that's liquid evaporation. And we have chosen a configuration which is the easiest to deal with. So it's a single isolated droplet in an infinite quiescent atmosphere of oxidizer. So the droplet is not moving, there's no flow in the oxidizer, there's no effect of gravity, and we have also additionally taken a few more simplifying assumptions like constant properties and things like that. So we discussed all the assumptions yesterday in detail. And where we stopped yesterday was with the droplet surface energy balance. And to refresh your memory, I'll show you what we had written yesterday. So if you take this droplet and try to do an energy balance, then you identify the energy flows to the surface from different directions. So we have this m dot h liquid, that means liquid is moving from the interior of the droplet to the droplet surface, and that energy is m dot into h liquid. And similarly, there is fuel, in fact fuel vapor, which is leaving the droplet surface and going into the gas phase. So we marked this as m dot into h vapor. So this is the vapor enthalpy, h vapor, and then we also wrote a q dot term. So q dot term is the energy which is getting added to the surface. We thought about it yesterday. This is primarily by means of conduction, and we are neglecting radiation. We have higher temperature in the gas phase. So this can be the temperature of furnace gases. So there's a droplet which is entering furnace. Furnace already has something burning in it, so it has high temperature, and this temperature T infinity corresponds to that sort of a furnace temperature. And then we have this droplet which is at a colder temperature. So this is at a temperature of, let's say, the room temperature, and it enters the furnace. So it will get heated and its temperature will get raised to its boiling point temperature. This is the assumption that we made, and we are doing a simple calculation, but if we do a more detailed calculations, it's possible to show that it will reach very close to the boiling point temperature. Now the temperature T infinity may be much higher, maybe the furnace temperature may be 700 degrees Celsius, maybe more than that, so 1000 Kelvin, maybe more than that. But the droplet temperature initially is probably room temperature, which is 25 degrees Celsius, 27 degrees Celsius. It gets raised to its boiling point temperature. I mentioned yesterday that for normal heptane, the boiling point temperature is 98 degrees Celsius. For normal hexane, N-hexane, I think it is 69 degrees Celsius, okay, at atmospheric pressure. And it reaches the boiling point temperature, so it gets heated to some extent, but we are making this assumption that it gets quickly heated to the boiling point temperature, and it's also at more or less the uniform surface temperature. So the q dot conduction that we are talking about here is coming from the gas phase. We are neglecting radiation, and it's happening through the process of conduction. So this temperature gradient enables conduction of heat to the surface. So we could write this balance, q dot conduction plus m dot h liquid equal to m dot h vapor, and from that we wrote q dot conduction equal to m dot h fg. We did that yesterday. Now what do we plan to gain out of all this? What is our purpose again? Our purpose is to get m dot. M dot is the mass loss rate, isn't it? It's actually the mass flow rate in the domain. We saw yesterday that this m dot is equal to m dot of fuel, because m dot is constant according to our assumptions. We made a very important assumption yesterday. We said that we are tackling a quasi-steady problem, right? And we have, in that case, if we are writing this kind of a balance, then actually what we are interested in is to get m dot. Finally, that is our objective. Now, does this help us to get m dot? What do we have now? We have q dot conduction is equal to n dot hfg. So we are writing this equal to m dot into hfg. M dot into hfg is what we are writing. So we are equating these two things. Does it help in some way? we want something for m dot which we can use, some expression for m dot which we can use. So, we can see that will be able to write m dot in terms of dt dr at r equal to rs. Right? Is that good? Does it help us? Do we have dt dr at r equal to rs? No, but we know how to get it. Okay. Again, this we had done yesterday. This part written in red, this was the energy equation and these two are the boundary conditions. So, we started with the Schwab-Zeldovich form of the energy equation in spherical coordinates. So, that was this one and that was this one, and from that, taking constant properties and things like that, knowing m dot equal to constant, we know that this is the energy equation and we understand that this energy equation can be integrated easily. It is not very difficult to do this. And we also have boundary conditions. We know that far from the droplet the temperature is T infinity, that furnace gas temperature, and at the droplet surface it is T boil. R equal to Rs is the droplet surface, right. So, this can be integrated. If we integrate this, we will get what? We will get temperature as a function of R. All this should be able to give you temperature as a function of R. And once we get that, we can do dt dr at r equal to rs. So, that is good news, because once you have dt dr at r equal to rs, then you have something for m dot, correct. So, we can get m dot as a function of let us say this rs. So, m dot expression will have hfg, it will have rs, it will have kg. Now, we are not going to find out this dt dr at r equal to rs explicitly, that is done in Turns's book. Okay, so, you can go through that.
In the previous expression, the equation for T, m dot was there. So,
yeah.
T will be in terms of m dot will be.
Yeah, that does actually, yeah, that does not really matter, because we will be able to integrate and get T. So, his question is that okay, T will have m dot itself, but that will not matter, because ultimately we can extract m dot. Okay, that is the idea.
Means that in the dt by dr terms, m dot term will be there.
Yeah, yeah. But that is not a problem. Okay, so his question is that the differential equation that we have for energy, okay, the one in red just shown you a few minutes back, this has an m dot. So, if we integrate this and get T as a function of R, you will get m dot somewhere in the expression. But that does not matter, because m dot is a constant. So, we will not have any difficulty dealing with it. So, we will be able to extract first from T as a function of R, we will be able to extract dt dr at R equal to Rs, okay. And then finally, we will be able to solve for m dot. That is what I am interested in highlighting here. So, I am leaving out the details. I am leaving out the details of getting T as a function of R, evaluating dt dr at R equal to Rs, getting expression for m dot. Okay. So, I am leaving out. Because you can see Turns's book and it is fairly straightforward. I already told you the equations and what integration to do. It's pretty simple. So, ultimately, using what we had few minutes back, m dot into hfg equal to okay, so this is kg, not in kilogram, not as in kilogram, but this is k thermal conductivity of the gas phase, right. So, we can do all this and then we can get an expression for m dot. M dot expression is Okay, so this is m dot, and this is good because we can get kg, we can get cpg, we can have some representative values of the properties kg cpg, and we know T infinity because that is the furnace gas temperature, and T boil we know, HFG we will know, so we can calculate m dot. That is the whole idea. And to tell you a little bit more about the properties, we have CPG which will evaluate at as the Cp of the fuel, F for fuel, at a temperature T bar. I will tell you what T bar is. And we have Kg sorry, this is K infinity actually. Maybe I should write this again. 0.6 K infinity T bar. And T bar is T boil plus T infinity divided by 2. Now, where does this come from? This people have found that if you take this sort of values, then you get better accuracy in predicting m dot. So, this I think came from a research paper by a person called Williams. That is not very important. Just need to know that okay, how do we get CPG? We get Cp of the fuel and evaluate at a T bar. What is T bar? T boil plus T infinity divided by 2. Similarly, there is something for Kg. So, this K infinity I think is the oxidizer thermal conductivity evaluated at T bar. Okay. So, this sort of thing. Look this up. There is example problem in turns also. So, that will help you get a feel of the numbers. So, see example problem. Okay. Now, one more point here. This quantity has a name. This is written as a BQ, and this is called a B number, or it is also called a Spalding number. So, this goes by the name of Brian Spalding. It is also called a Spalding number. So, it is log of B plus 1. M dot is proportional to log of B plus 1. So, this B plus 1, log of B plus 1 is kind of like a driving force for generating m dot. Okay. So, this is a Spalding number, or also called a transfer number. When we go to droplet combustion, we are going to see something very similar, and we are going to get another B number. This is B number for evaporation situation. Okay. So, we can get m dot, but it will be a little bit more interesting if we also find out some expression for droplet lifetime. Once you get m dot is the, so you have this droplet and there is this m dot, okay, mass flow rate around the droplet. We saw that that is constant within the constraints of our assumption, fine, and we said that that m dot is equal to m dot f. So, this tells you that if we find m dot, then we have found m dot f, which is the fuel mass flow rate. Okay. We know that the fuel actually flows out from the droplet surface with some velocity, radial velocity, which we called Vr, isn't it? In fact, we wrote m dot yesterday as 4 pi r squared into Vr. So, we did that, and we understand now because of the expression that we derived today that we can find m dot, but once we find m dot, we can also find out droplet lifetime, because of course these two are related. Why is droplet lifetime important? Droplet lifetime gives you something in terms of fraction of a second, okay, some millisecond or maybe even of the order of second if the droplet is large. So, it gives you some time over which the droplet will go from the initial droplet diameter to a 0 diameter. Basically, the droplet will get consumed. Droplet will evaporate. Why is that sort of time scale important? Because as we discussed in the case of engines combustion, if you are producing a spray, then you are actually sending a lot of these droplets into the engine combustion space, and then those droplets have to evaporate quickly and then they also burn. So the time that these droplets require for evaporation is an important thing, right? Because we want to evaporate them quickly and we want to burn them quickly, and only then the engine processes will be effective, because you are trying to do this combustion to generate these hot gases, which will push the piston down, as I was telling you yesterday. So we want to get the droplet lifetime, and it will come from m dot, of course. So for droplet lifetime, we can write d dt of mass of droplet equal to minus m dot. So what is the mass of droplet? It is rho L into pi d cubed by 6. Capital D is the droplet diameter. Rho L is the density of the liquid. We had rho's in some other equations, but that's like the gas phase rho, isn't it? The gas phase there is a density, which we call the rho, and for the liquid density we are using the rho L notation, L for liquid. So the mass of the droplet is, of course, rho L into pi d cubed by 6. So we can put that in here and we can get an expression for D. What else should we also do? We should also write for m dot, we should use the expression that we already have. Okay, and thereby we will derive a rule, a law for the variation of the droplet diameter with time. Okay. So note that this time we have brought in the they've brought in time, isn't it? This gives you time. Till recently, we wrote expressions where we didn't have time, because we took quasi-steady and then we dropped out the del t terms and things like that. But now we have brought in time because we want to see, based on our simple theory, how the droplet diameter will change with time. Okay, so this goes in here, and for m dot, we use the expression that we already have. And with a little bit of effort, which again I'll have to ask you to do, ask you to check. So leave some space in your copy where you are taking notes, so that from here you can verify whether this happens or not.
Sir, m dot is mass of fluid.
M dot is that mass flow rate, which we said also is equal to m dot f, and for which we have found that expression. So we had shown that this m dot over the domain actually remains constant. So if it remains constant, it will be the same as the value that of m dot that you get at the liquid vapor interface, which is at the droplet surface. Correct? So we have this expression. So we use m dot, and you can see that we have used that m dot, because now in the expression you see bq, which is that b number. So we use that. And we can also play a bit of a trick, because we can take this d, this diameter can come here. Okay. How did this d come? Because the m dot expression has an rs. M dot expression has an rs, which is the radius of the droplet. So I replace that by capital D by 2. So that we get everything in terms of the droplet diameter. Okay. So if you produce a spray, you don't talk in terms of droplet radius. You speak in terms of droplet diameter, isn't it? Micron level, millimeter level, whatever. But these are all diameters, so it's better to get an expression in terms of diameter. So we can take this d here, and if we get that, we'll get d dt of d. So that we can translate easily in terms of d squared. So we'll get d squared. And again, please do all these steps at home. So this is b subscript q. I mean, the way I've written it looks like b into q. Not correct. This is b subscript q. So that's a useful expression. And this thing, which you see on the right hand side, can be given a name minus k, and k is an evaporation constant. Okay. So this part without the minus sign is the evaporation constant. So that means we are saying that d dt of d squared is equal to minus k. So that means d square is equal to d naught squared minus kt. Correct? So what is d naught? Initial droplet diameter. So this is good because this tells you that if you can find out m dot, from that you can find out k, which is the evaporation constant. Then you can find out how d, the droplet diameter, the instantaneous droplet diameter. Droplet diameter is changing because the droplet is bigger, then it keeps getting smaller. So the droplet diameter is changing. And how the droplet diameter is changing is described by this, which is called a d squared law. So this is important. In combustion literature, this is known as a d squared law. In fact, this is d squared law for evaporation, and we will also subsequently find a d squared law for combustion. So there is a d squared law for combustion also, which will look somewhat similar. Okay. So this is nice. Comes from m dot, but it's something which appeals to you more because it's pretty easy for you to see that d squared actually linearly decreases with time. Okay. And if you want to plot that, so you will get d squared as a function of time, and the slope is minus k. So that's why you write d squared equal to d naught squared minus kt. So the droplet lifetime is of course d naught squared by k. Fine. So if k is higher, then the droplet lifetime is smaller. And when is k higher? What is k again? K is, where did I keep this k expression? Yeah, this is here. Here is k. Yeah, so here it depends on properties, but it also depends on this b number. Okay, and the b number is, as you have in your note somewhere, it's Cp into T infinity minus T boil divided by HFG. So if you have, let's say for example, higher T infinity, then the B number will be higher, and if the B number is higher, then the K is going to be higher, and if the K is higher, then the droplet lifetime will be smaller. Again, in a lecture we cannot spend too much time on this, but you need to look up examples in the book where droplet lifetime calculations are done. Then you will see what is the order of magnitude of droplet lifetimes. So if you have a micron sized droplet, do you get 10 seconds as droplet lifetime, or 1 second as droplet lifetime, or a fraction of a second as a droplet lifetime, or milliseconds as a droplet lifetime? So we need to do that as exercises for different kinds of fuels in different atmospheres. So that will give you a feel for these numbers. So this is what we wanted to do with regard to droplet evaporation. Droplet evaporation is an easier problem which we wanted to work on. We saw that actually the equations are pretty simple, right? The only thing we needed was this mass conservation equation, of course, to show that m dot is equal to constant, and also the Schwab-Zeldovich form of the energy equation, which of course involved some work, but we had done that work for a planar flame long time back when we were doing premix flame analysis, isn't it? So we had done the Schwab-Zeldovich form previously for planar flames for 1D Cartesian coordinate. But for spherical situation, we just picked up the Schwab-Zeldovich equation from the book and then used that to get the energy equation, and simply integrated this between the droplet surface, that is r equal to rs and r going to infinity. And from that we have essentially got what we wanted. We got m dot, and we also got the d square law and the droplet lifetime basically. So now we have to prepare for something which is more interesting for us, and that's droplet combustion. It is going to be somewhat more difficult, but not much more complicated, not a whole lot more difficult than what we have done for droplet evaporation. And to appreciate what we want to study, first let's think about what we want. Again, same thing, right? What is it that you are interested in? You again want m dot, and you again want the droplet lifetime. And you just want to have expressions which will give you m dot and the droplet lifetime, and hopefully they will also tell you how combustion is different from the evaporation case. Okay, so our objective is kind of the similar situation. Is it going to be more complicated? Let's think about it. I had drawn something yesterday, like this droplet with this radius, and I actually told you that if you have combustion, then we are going to have this red thing here, which is a flame, correct? And I said that blue for colder, red for hotter. So low temperature here, higher temperature here. And additionally, you can think about it this way, that if we say that the reaction rate is really high, then we will say that this zone is actually infinitesimally thin. Correct? Again, from our diffusion flame understanding. We discussed this quite a bit then. So we will expect that the temperature will be something here, maybe close to the boiling point temperature, and it will go up in this region, and then it will drop down to T infinity. So how high can this T infinity be? Of course, it can be the furnace temperature, but you can also burn droplets in temperatures which are much lower, like ambient temperature. You give a spark near the droplet, and then it will establish a flame. Okay, so colder ambient, oxidizer atmosphere, so the droplet in an oxidizer atmosphere. But I am saying that the oxidizer need not be at furnace-like temperatures of 1000 Kelvin, 1100 Kelvin. Need not be like that. It can be closer to room temperature, but you give a spark, and then it establishes a flame. So in that case, the T infinity which you see in this particular curve that I have drawn, okay, this T infinity can be the room temperature also. So you have given a spark and produced a flame. Once you have got the flame, then you can get this sort of a profile. This is thin. And we can also bring in our understanding of infinite reaction rate situation and think about what will happen to the fuel mass fraction profile and the oxidizer mass fraction profile. Again, you expect that the fuel mass fraction will drop down to 0 here, and the oxidizer mass fraction will drop down to 0 here, because they will get consumed at the flame. So again, the same sort of situation. Oxidizer may not be able to cross over to the inner zone. What is the inner zone? We can call this inner zone, that is between the droplet surface and the flame, and the outer zone is between the flame and till infinity basically. Outer zone is from the flame to outside, far away from the droplet. So we expect that the inner zone will not have oxidizer and the outer zone will not have fuel, correct? Again, same discussion that we had for diffusion flame. So high reaction rates will ensure this. So we are interested in m dot as always. How will we get m dot? How did we get m dot for the droplet evaporation case? We did a surface energy balance at the droplet, isn't it? At the droplet interface, droplet and vapor interface, okay, liquid vapor interface. We did a surface energy balance, and through that we could get m dot. We used dTdr at r equal to rs. So we just said that okay, it's all transfer is by conduction. There's no radiation involved. So we can do similar thing. Okay, what are the complications that you envisage in that case? Yeah, so now we have reaction. So in that case, energy equation could be solved easily. We had this Schwab-Zeldov which formed the energy equation. Just placed a boundary condition of T equal to T boil at the droplet surface and T equal to T infinity, T approaching T infinity far away from the droplet. These two boundary conditions were fine. But now what is the problem? Now if you look at this picture, this temperature profile will determine the conduction heat flux into the droplet. Okay. And to know this temperature profile, you need to know where the flame is and what is its temperature. So it's going to be more involved. But if you can get this temperature profile, then we can again do dTdr at r equal to rs, multiply it by thermal conductivity, okay, and the area of the droplet to know how much heat is going into the droplet, and then thereby relate that to the evaporation rate of the droplet. Now this evaporation of the droplet, the liquid fuel is getting evaporated in the presence of combustion. Okay. So it's going to be more complicated, and we will have to bring in the fuel species equation and oxidizer species equation and energy conservation equation to solve these together to actually know which one is going to be this profile. Okay, so it's going to be more involved. So we'll be interested in m dot definitely. M dot is same as that m dot f, but to get this, we will be forced to get the flame temperature. We will be forced to get the radius of the flame. Okay, we'll be forced to, isn't it? And in fact, in this problem, we will also say that the droplet temperature will not beforehand assume it is the boiling point temperature. So we will say that the droplet temperature is Ts, and there is a fuel mass fraction profile which will also get established here in this region, and that fuel mass fraction at the surface of the droplet will call YFS. So these will also have to be determined. It's not like we want to get everything, but we'll have to get these in order that we are able to get m dot. Okay, so we have to bring in m dot somehow. To get m dot, some of these other things will also come. Now, just to make sure that we keep this physical picture of the droplet in mind, the first thing we will do here is similar to what we did for the droplet evaporation problem. So we will take this droplet and do an energy balance, essentially getting something very similar. So let's say this is the droplet surface. Okay. Now drawing it just as a line. Okay, so it's just a tiny part of if you have the droplet, look at this tiny part and then expand it, then you get this line. Okay. And this is as before, m dot f into h liquid, and this is as before m dot into h vapor. And there is a q dot gas to interface. Okay. So that will be again similar to what we have seen before, and there can be in fact a q dot I to L. I to L. I means interface. So this was gas to interface, and this one that we are writing, this one here, it's interface to liquid. Interface to liquid. So these can all exist, but actually we'll later see that depending on what assumptions we make, we can actually get rid of this q dot I to L if we say that the droplet is more or less at a uniform temperature. See, these are like tiny droplets, so they are likely to be at any instant of time, they're likely to be more or less at uniform temperature. If you just bring in a droplet in an atmosphere where there is a hot gas or maybe just given a spark, then initially there is a droplet heat up period, isn't it? So droplet at 25 degree, this will get heated, but it will go towards a boiling point, isn't it? But as it approaches the boiling point, it will, so that's the heating up period, and as it does, it will tend to get heated if the droplet, especially if the droplet is small, it will tend to get heated in such a way that at any instant of time the droplet temperature is more or less uniform. Okay. So what I mean by that is that, okay, at some time the droplet temperature may be okay, this is r equal to 0, let's say, smaller at the center and then larger as you move away from the center. Okay. But it will, that's at very initial times, but then it will tend to become more uniform and it will keep increasing with time. But it increases with time, but still it's more or less uniform over the mass of the droplet because the droplet is really small. So we can use that sort of argument, and if we use that sort of argument, then this q dot I to L can be set equal to 0. Now we can understand that it should be possible for us to write this in general. If q dot I to L is 0, then q dot G to I is same as m dot f h f g. So q dot I to L is 0, assuming heats up to a steady temperature Ts. Okay. So what about q dot G to I? Again something similar. This is a conduction heat flow to the droplet. So this will again involve the dT dr at r equal to Rs, right? Okay. So our main concern is now to get the energy equation with boundary conditions and try to solve those, because we understand that our problem is more complicated because there is a flame in between, but we still need to get, most importantly, the temperature variation with R in the inner zone. Inner zone means from the droplet to the flame. If we get that temperature as a function of R, then we can calculate dT dr at r equal to Rs. Okay. So what is our energy equation? Energy equation is going to be very similar again. So I'll just write the energy equation, which is the Schwab-Zeldovich form, constant properties like before. Just as a shorthand to make notation simpler, Turns has called this part that I've encircled, he has called it a ZT. Called it a ZT. So you can integrate this. This ZT is important because if you take constant properties, this is actually constant. ZT is also a constant. M dot F is also going to be a constant. Okay. How? Same logic. You take the conservation equation, mass conservation equation, and similar to the way we had shown it for the liquid evaporation case, we can show, just by integrating, we can show that this m dot will be constant. Okay, so m dot equal to m dot f equal to constant. So this can be used. And integrating this, we will obviously get T as a function of r as so this is very easy stuff. Remember, we are talking about the combustion situation. Okay, talking about the combustion situation. So how much is this one? This is Rs. This we are calling Rf, right? This temperature here is Tf. This temperature here is Ts. Fine. S for surface, F for flame. That's a notation.
Do you say Ts is equal to T boiling?
No, in the combustion example, we are actually not doing that. Okay. That requires some discussion. May not be able to do it today, but definitely in the next class. Yeah, so we are saying that we will find out Ts. So the question was, are we saying Ts equal to T boil? In the combustion problem, we are actually not saying that. Okay, and the reasons behind this, we'll discuss that in the next class. But Ts is something which we are trying to find out from the solution of different conservation equations. Okay, so we'll come to that slowly. As of now, Ts is not equal to T boil, right? So at R equal to Rs, you have temperature of Ts. Yeah.
This energy equation is only valid in the region between the droplet surface and the flame, right?
No, this energy equation is actually valid at different places in the inner region as well as in the outer region, but you have to integrate separately. I mean, you have to use the boundary conditions separately. Okay, right. So I have to reiterate what we did for diffusion flame jet example. So his question, the question that he's asking is, where is this energy equation valid? This energy equation is valid in the inner region as well as in the outer region, and we are not bothering about the flame. Okay, so his question is, why don't we have a source term here? We don't have a source term because actually we are assuming an infinite reaction rate. If you assume an infinite reaction rate, then the flame is just a boundary. Flame is an infinitesimally thin surface, so it's a geometrical surface. Because the reaction rate is infinite, the thickness of the reaction zone is extremely small. How small? Infinitesimally small. If some thickness is infinitesimally small, then it's just a surface. Okay. So the flame in this case actually serves as a boundary for the inner and outer regions. So it's that surface. Flame is now a surface which just separates the inner region and the outer region. So its only job is to provide a boundary condition. So the reaction rate term need not be considered. So what I'm saying is, we are solving, this equation is valid everywhere, okay, but we are not considering the flame. Flame is just serving as a boundary. So this equation we are taking in this region, in the inner region, and this equation we will also solve in the outer region, everywhere. Flame just sets up the boundary conditions. So what are the boundary conditions? Very easy. See, you need boundary conditions to get this C1 and C2. So, for the inner region, the inner zone, R equal to Rs, T equal to Ts. R equal to Rf, T equal to Tf. And outer, again R equal to Rf is T equal to Tf, and R tending to infinity, T will tend to T infinity. So this flame actually serves as a surface where we can supply boundary conditions, but it also makes it discontinuous in the sense that you solve the temperature profile in the inner zone and solve the temperature profile in the outer zone. They will give you the same temperature at the flame, that's all, but these are like two pieces which are coming from two different zones. And what am I talking about? I am talking about, okay, we have already qualitatively seen these two pieces. Basically what I mean is you are matching the temperature here. Okay. The inner zone energy equation, when integrated, it will give you a temperature Tf. We are ensuring that by forcing a boundary condition here of T equal to Tf at R equal to Rf. Similarly for the outer zone. So you get one piece from the inner zone solution, one piece from the outer zone solution. So are we actually going to do this in detail? Again, no. So we are not going to solve this equation for the inner and outer zone separately, because again I think you can handle this. You can do it on your own. So for me it is just sufficient to say that we get these two pieces of T as a function of R. These two match at the flame. Correct? Now, if you think about the whole situation, we want m dot, isn't it? M dot will give us droplet lifetime. That's the most important thing. But there are other helpful things we would like to know. We'd like to know where the flame is, where is how much is the value of Rf. So we have a 50 micron droplet of heptane and it produces a flame. So where is the flame? What is Rf? So that's an interesting question to answer. So we'll try to get that. And what is the temperature of the flame? Of course, temperature is important. Okay. We're talking about combustion, so we want to know what's the maximum temperature that we get in the domain. So that Tf happens at R equal to Rf, so we'd like to know that. In order to get m dot, we understood that there are complications involved because we have to get this temperature profile and also fuel mass fraction profile, oxidizer profile and all that. Ultimately, we will not get m dot in isolation. To get m dot, we'll have to get a few other things like the flame temperature, the radius of the flame, the surface temperature of the droplet, and the fuel mass fraction at the surface. Okay, so we have to get all this, and for that, of course, we need other equations. How many equations do we have now? We have actually we got the temperature profile, and with the help of that we can get a droplet surface energy balance. Okay, so that's one equation that we have which we can use. Where is that? That is, I wrote somewhere. Yeah, that's if q dot IL equal to 0, then it's just this, and this has dt dr at r equal to 1. So this is one thing that we have got. Okay. We'll have to develop more equations. Again, we are running out of time, so it will be hard for me to convince you what are the other equations that need to be derived in the next 2 or 3 minutes. But before we do that, there's one interesting thing that I would like to bring up. In the droplet evaporation problem, there were no products. Okay, just fuel gets evaporated and gets it moves away from the droplet. Actually, there is a flow which is induced by the evaporation process, and it just moves out away from the droplet. Okay, and that process keeps on happening. Now here, of course, there are products also. So what do the products do? Like in a diffusion flame, the products will get produced at the flame, right? And the products will move out in this direction, but the products will move out in this direction also. Okay. And the fuel will go in this direction, and the oxidizer will come in this direction. Okay. There's one tricky thing about the products which I want to mention now before we go to detailed equations in the next class. So we'll assume that these products will not go and get dissolved in the liquid fuel. Sometimes that can happen, but typically it will not happen. So these product gases, these are gases, we'll say that they have zero solubility in the liquid fuel that we are considering. So that's a reasonable thing to say. And if they do not get dissolved in the liquid fuel, then they are getting produced here, but they will just establish a product mass fraction profile here. Okay, higher value at the flame, smaller value at the droplet surface, but there will not be a flow of products as such, a net flow of products into the droplet. Okay, so it just forms a stagnant layer. It forms a stagnant layer. How is that different from, let's say, the flow of fuels, like fuel? Fuel goes here and gets consumed. Okay. So it keeps moving. Right? Products will just form a stagnant layer. Why? Because there is no sink. It will not get dissolved into that liquid. So just form a layer and that's it. Products will form a stagnant layer and the fuel will diffuse through that stagnant layer. Correct? Fuel has reason to move because there is more fuel here near the droplet surface, and at the flame fuel concentration goes to 0. So this will keep moving, keep getting consumed. But the product is not getting consumed, product is getting produced at the flame, but not getting consumed anywhere. So it will form a stagnant layer. Okay. So this will be important in the later discussion.
The product mass fraction will keep on changing with time. Means the profile will change.
Yeah, but we are trying to solve in the quasi-steady region. Okay. So we'll maybe in the context of this we have to understand the quasi-steady assumption better also. So it will give you Y product as a function of R, which in the context of our model framework is not changing with time because there is no time in the equations. When will time come finally? Time will come when we try to write the droplet lifetime equation. We wrote ddt of the mass of the droplet equal to minus m dot. We did that for droplet evaporation. Of course, we can do it for droplet combustion also. Correct? So that's when time will show up. But right now in the next class, the equations that we wrote and the energy equation that we wrote, there was no time. Okay. So that is because of the quasi-steady approximation. All right. So we'll stop here.